We've already seen how there are parallels between rotational motion and translational motion. We have a one-to-one correspondence between the descriptors of rotational motion with the descriptors of translational motion. What I mean by that is x in translational motion becomes theta. V in translational motion becomes little omega, the angular velocity. Acceleration, linear velocity, becomes alpha, the angular acceleration. And there's this simple connection between all of them, that the linear one is just the angular one times r, where r is the distance from the rotation. Well, there's also a rotational version of force called torque. And torque refers to a force that has the effect of changing the state of rotation of an object. Remember that Newton's laws of motion tell us that it takes a force to change the motion of an object, in other words, the acceleration. Well, it takes a twisting force or a torque to change the rotational motion of an object. So some forces do not exert torques. So in the slide here, you see a door looking down from the top. The hinge on the left there is the axis that it can rotate around. And the force F2 is a force applied to the edge of the door, does not cause the door to rotate. So the torque from F2 is zero. You can go to a door and push on it towards the hinge and you'll see it doesn't make the door rotate. Also, there's a reason the doorknobs on doors are placed as far away from the hinges as possible. F1 and F4 are the same magnitude force, but F1 is going to make that door open faster than F4 is. It's easier to push the door open when you're pushing far away from the axis of rotation. So on the other hand, F3, which is also applied out at the end of the door, does not make the door open as fast as F1 does. So there's all those three things at work that determine the torque or the twisting force that's acting on an object and how its angular rotation changes. So we will go through that, but basically the torque, and we use the Greek letter tau, is the distance from the rotation axis that the force is applied times the perpendicular component of the force to uh, the line connecting the axis to where the force is applied. So that's illustrated here in this slide, where you can see there's the pivot point is the center of the wrench. The force is applied out at the end of the handle, a distance r away from that pivot point, and it's applied at some funky angle. What we want is the component of that force that's perpendicular to the line r. And from looking at that, you should be able to immediately see that that perpendicular force would be F sine phi in that particular example. And here we can see that F perpendicular is F sine phi. The parallel component of that force, which is F cosine phi, is in the direction of the axis, so it doesn't make the thing twist at all. So it's irrelevant for the twisting motion or the torque. There's a second way that you can calculate it instead of doing the full distance out times the perpendicular component of the force. You can take the full magnitude of the force, then times something I'm labeling here as r perpendicular, that they're calling the moment arm. And the slide here shows you geometrically how you calculate that. But basically, you can see that that r perpendicular from the triangle that's shown in the figure is r sine phi. So either way, in this case, you get r times f times sine of phi. And again, please don't remember, oh, it's times sine of phi, because that's true when the angle is drawn the way it is, but that's not necessarily the angle that you'll always be given. But if you've got the angle between the force and that lever arm vector, then it is rf times sine phi. So if the angle between the force, and I'm going to put a vector symbol over that r, is phi, then torque is rf sine of phi, where things look like this. I'm just going to draw a beam. Here's our axis of rotation. And let's say that we apply a force here. In some random direction, then this is r, and so the angle phi is this angle. Okay, I would have to pick up my r, slide it out here so that it's starting at that same point. So in that case, then the torque is rf sine phi. Let's step forward and go ahead and work through an example so that we see how this works. Revolutionaries attempt to pull down a statue of the great leader by pulling on a rope tied to the top of its head. The statue is 17 meters tall, and they pull with a force of 4,200 newtons at a certain angle. What is the torque they exert on the statue? So first, let's draw a picture here. So here's a statue. Looks just like a person. And people are pulling down on it at an angle of 65 degrees to the horizontal. So here are the people pulling with a rope that's tied to the head here. So that's our force vector, and it is 65 degrees to the horizontal. This is 17 meters, and this angle is 65 degrees. Okay, so the question is, and the force, we're told that the force, the magnitude of that force is 4,200 meters. And the question is, what's the torque, and is it positive or negative? The question says if they're standing to the right of the statue, and I drew them standing to the left, but we'll worry about that when we get to part B. So the torque is rf sine phi, but here's where we got to be careful about those angles, because this angle is relative to the horizontal. This is not phi. This line here is not the r vector. That's why it's so important that the angle phi is the angle between the vector and the line connecting the pivot point to the force. So let's redraw this simpler with replacing the statue with just a bar, and it's going to be toppling over, so it's pivoting around this point. Here's the pivot point. And the distance, oh shoot, the distance here, this is my r is 17 meters, and it's pointing up, right? So phi, if I want to use r sine phi, is this angle here, okay? And if I draw a horizontal line here, I know that this angle is 65 degrees. That means this angle is also 65 degrees. So that means that phi is 90 plus 65, or 155 degrees. Okay. Then I can go ahead and calculate the torque is 17 meters times 4,200 newtons times sine of 155 degrees. And let's see what that works out to be. degrees, and I get 2,480 Newton meters. And a torque is always a force times a distance, so it always has units of Newton meters. So that's the magnitude of the torque. Part B of the question said, if people are to the right of the statue, is the torque positive or negative? So let's just redraw it again, but this time we'll put the people on the right side. Here's my force. Here's all the little people down here pulling over the statue, so it's rotating this way. That torque would lead to a rotation in the clockwise direction. This torque, shown above, would cause a clockwise rotation. Clockwise is negative. As shown on the previous slide, I had them on the left. That would cause the thing to be rotating in the counterclockwise direction, which would be a positive torque. Rotation caused by the torque would be counterclockwise, so it is a negative torque. It is important to have those because there are situations where you can have something pushing something one way. This would be causing clockwise rotation, and something else pushing in the other way, which would be causing counterclockwise rotation. Those have opposite signs, and so they can cancel each other out. So there can be multiple torques acting on an object, and they can add together or they can cancel each other out depending on their sign. The sign of the torque is given by whether or not the rotation that torque is going to produce would be a positive or negative rotation.